So, in lecture 5, I will discuss about the penetration test or standard penetration test. In the previous lecture, I have discussed about the direct method or the test pit or the trench pit or the semi direct method where we are collecting the soil sample by boring. So, there are different methods by which we can collect the soil samples, and here this is the indirect method. So, that is the standard penetration test. So, this test is very important because we are using this test frequently to determine the soil properties. So, why it is called the indirect method? Because in the first method it is direct method, because we are collecting the soil sample directly from the site. But it is the indirect method, here we are not determining the soil properties in terms of that our strength properties or any other properties. Actually, we are measuring something else, and then we are correlating that that measure value with our required soil properties, that is cohesion or friction. So, what is the standard penetration test? So, as I mentioned, it is the indirect method. So, the standard penetration test is widely used to determine the parameters of the soil or in situ soil. The test consists of a split spoon sampler into the soil through a borehole at the desired depth. So, and the split spoon sampler is driven into the soil at a distance of 450 millimeter at the bottom of the boring. A hammer of 63.5 kg weight with a free fall height of 750 millimeter is used to drive the sampler. So, that is why these things are standard. Your height of fall is standard, that is 750 millimeter, and the hammer is also standard 63.5 kg. So, I am describing this method is as per the IS 21301 1981. So, basically what we are doing here, we are driving a split spoon sampler into the soil up to 450 millimeter in 3 stages, 150 millimeter, 150 millimeter and 150 millimeter, and with a hammer blow of weight 63.5 kg and with a free fall of 750 millimeter. So, the number of blows for a penetration for last 300 millimeter is designated as the standard penetration value or the number n. So, basically we are measuring here the n value. We are not measuring the cohesion or the friction, we are measuring the n value, and then we will correlate this n with the cohesion and the friction or any other properties of the soil. So, that is why it is a indirect method. So, as I mentioned, we are applying we are applying a hammer blow on a split spoon sampler and allow this sampler to penetrate up to 450 millimeter in 3 stage, equally 150 millimeter. But we are not collecting, we are not counting the or considering the first 150 millimeter penetration, because that is considered as a sitting load. So, basically if I place this hammer this split spoon sampler for a particular on a particular depth into the soil, and if I apply blows and allow this sampler to penetrate for 150 millimeter. So, it will require some number of blows. So, with a standard weight of hammer and with a standard free fall. So, we will count those blows for first 150 millimeter, then second 150 millimeter and third 150 millimeter. But we will not consider the first 150 millimeter n value or counted blows, but we will add the second and third 150 millimeter penetration blows, those are required, and then we add those things. That means, if we say the number of blows required for first 150 millimeter penetration is N1, and the number of blows required for second penetration for 150 millimeter is N2 and third one is N3. So, the N value will be N2 plus N3. So, this is, as I mentioned, this is performed in 3 stage and the blow count is found every 150 millimeter penetration. So, the blows for first 150 millimeter are ignored as these required for the seating drive. So, this is the one animation that we have. The free fall is 750 millimeter or 75 centimeter, and this is the hammer 63.5 kg, and this is the sampler tube that we are applying blows. So, we are allowing this split pun sampler to penetrate for 150 millimeter, 150 millimeter, 150 millimeter. So, that is the number of blows for first 150 millimeter is N1, second 150 millimeter is N2 and third one is N3. So, the standard penetration resistance or SPTN is N2 plus N3, and the number of blows the first 150 penetration, as I mentioned that this is not considered for, as it will act as a seating load. So, the test can be conducted for every 1 meter vertical interval, not more than 1.5 meter. So, I have a couple of YouTube videos by which you can see that this is the drill rod. So, in the bottom of this drill rod, this sampler tube is attached. So, this is the sampler tube. So, it has the two halves. So, this is the soil sample they are collecting. So, this is the drill rod. So, as I mentioned, so you can increase the depth of this or the height of the drill rod by adding one up to another. So, you can go up to the required depth. So, this is the tripod kind of thing which is used for the penetration purpose. So, this is the drill rod. So, once this is the sampler tube that is attached with the drill rod, and then this is the sampler tube. So, this sampler tube will be attached with the drill rod. So, first you have to go for the boring. Once the boring is done, so we attach the sampler tube with the drill rod. Then we will apply the hammer blow. Here this is the 3 marking are done. This is 150 millimeter. This is 3 marking, first, second and third. So, these 3 markings means each marking is 150 millimeter. So, because we have to count the blows required for each 150 millimeter penetration. Then this is the hammer blow which is applied. So, and at the same time for this number of blows is counted for every 150 millimeter penetration, because on this drill rod the 3 markings are given. So, these 3 marks basically indicates for 150 millimeter each. So, and then once this total 450 millimeter is driven into the soil, then this drill rod or the sampler tube is again removed or taken out from the borehole, and then we collect the soil sample. So, now it is the hammer blow is completed. Now, we are collecting this drill rod or the sampler tube will be taken out from the soil or from the borehole. So, for this test one borehole is required, and one particular depth or the required depth. Once the borehole is constructed, we place the sampler tube and we attach this sampler tube with the drill rod, and over the drill rod we apply the hammer blow, and then we count the number of blows required for each 150 millimeter penetration, and this is the sampler tube. So, it is collected now. So, later on I will discuss about the detail about the sampler tubes, and because now once this is collected, so now it is removed. So, there is a cutting edge or that is removed, and then the soil sample will be collected. So, this is the, it has two halves. So, by opening these two halves you can collect the soil sample. So, this is the, this it has a cutting edge. So, that edge is first removed and then this sample is collected, because this is the two halves, this is the sample. So, this sample is collected from the required depth. So, the advantage is that in this test we are collecting the soil sample as well as we are measuring the N value or the SPT value. So, this soil sample which we are collecting, we can use it to determine the soil properties through the laboratory test, as well as we can we have the N value, that N value we can use to determine the soil properties also. So, we have another YouTube video by which also you can. So, this is another type of arrangement where this is the hammer and this is the free fall. So, hammer weight is 63.5 kg, free fall is 75 millimeter. Here this is the drill rod and where this hammer blow is applied, and in the bottom of this drill rod the sampler tube is attached. So, this is the another way we can conduct this SPT test. So, once it is done, now this drill rod with the sampler tube will be taken out from the soil. This is the drill rod and the sampler tube, this is the sampler tube which is taken out from the soil, and once it is taken out, then again the sample will be collected. So, this is the sampler tube, and first the cutting edge is removed, and this is the two halves, and this is the soil sample which is collected from the ground at a required depth. So, next one is that when the refusal of test. So, now if the 50 blows are required for any 150 millimeter increment or 100 blows are obtained for required 300 millimeter penetration, or 10 successive blows produce no advance, if any of them occurs, then we will stop this test, because you cannot proceed further with this test. So, these are the condition to stop the test, and then once we get the N value, that is the measured N value. Now, we have to apply some corrections over this measured N value. So, once we get the measured N value, so that means that one is measured N value, another is the corrected N value, and most of the correlations are based on the corrected N values. Sometimes the correlations are given with measure N values also. So, but the as per the IS code, there are two corrections we have to apply. So, one correction is the overburden pressure due to the, it is applicable for the granular soil only, and the next correction is the dilatancy correction, which is applicable for saturated fine sands and sealed. So, in one way, if the soil is clay, then we do not need to apply any corrections, but remember that this SPT is mainly suitable for sandy granular soil, but we can use it for the clay soil also. So, but people also sometimes use it for the clay soil, but any this I mean SPT is suitable for the sandy soil or the granular type of soil. So, now the corrected N value that you are getting. So, one correction is required for the overburden pressure, and because in the soil which is in upper portion the overburden pressure is less, but the soil where it is in very higher depth or the great depth where the overburden pressure is very high. So, that is why we have to apply a correction factor, and so you can see after applying this correction factor. So, the measured N value on the shallow depth will increase. So, that the corrected N value at the shallow depth is greater than the measured N value, and if it is the higher depth, then the corrected N value is the less than the measured N value. So, you can see that the corrected N value for the overburden pressure overburden pressure correction N dash is C n, which is correction factor, into the N is the measured N value. So, this is the C n value we will get from this curve. So, this curve is the correction factor C n, and this is the effective overburden pressure ton per meter square. So, you can see this if the effective overburden pressure is 10 ton per meter square. So, your correction factor is 1. So, exactly 1. So, that means, if it is 10 ton per meter square. So, the corrected N value and the measured N value both are same, but if your stress is less than 10 ton per meter square, that means for the shallow depth. So, this is the effective overburden pressure, as I mentioned the how I will calculate the effective overburden pressure, because you know that when we are calculating the effective overburden pressure. So, that is why that overburden pressure means the unit weight of the soil into the depth of the soil at the point where you are calculating that pressure. So, that means the depth of the soil and the unit weight of the soil. So, later on I will solve one example where I will discuss that how I will calculate the effective overburden pressure. So, depending upon the position of the water table, so if your effective overburden pressure will change. So, that means the effective overburden pressure means the unit weight of the soil into the depth of the soil. So, now if the stress effective overburden pressure decreases, so it means the if I say that the unit weight of the soil is constant, then definitely the depth decreases, that is why the effective overburden pressure decreases. So, at the shallow depth you can see the correction factor is greater than 1. So, the correction factor is greater than 1, because here your effective overburden stress value is very low, but at the higher depth the correction factor is less than 1. So, this is the zone where the correction factor is less than 1, which is applicable for the higher depth. So, and here this is for the lower depth. So, that is why we apply the correction factor C n, and once we correct this N value with the help of due to the overburden pressure. Now, if our N dash, so this N dash is the corrected N value after applying the overburden pressure correction, if greater than 15, then we will go for the second correction. So, if the N dash is not greater than 15, then we will not go for the second correction. So, what is the second correction? So, the second corrected after second correction, the corrected values N double dash is 15 plus 0.5 within bracket N dash minus 15. So, N dash is not the measured value, it is the corrected values after applying overburden pressure. So, then we can see that finally we will get the n double dash. So, now if you look at this expression, so suppose if our n dash value is 25. So, if it is 25, so what will happen? 25 minus 15 is equal to 10 by half. So, it is 5. So, 15 plus 5, 20. So, after applying the dilatancy correction, our measure n value will further decrease. So, if the n dash is 25, so after applying the dilatancy correction, it will become 20. So, we are reducing the n value further. Now, the question is, as we know that if overburden pressure correction is required as the overburden pressure is shallow depth is less and the greater depth is very high. So, we have to apply correction, you have to adjust the n value, and for the shallow depth you will increase the corrected n value, because it was under very less overburden pressure, but at the greater depth we will decrease the corrected n value as compared to the measure n value, because it is tested under very high overburden pressure. So, but why we will apply the dilatancy correction? So, that is a very important question. So, we are applying these corrections, but why we are applying these corrections? So, overburden is fine, because of the difference in overburden pressure, as the overburden pressure is different at different depth, we are applying the overburden pressure correction, but why the dilatancy correction? Now, the dilatancy correction, why it is required? To know that, we should know what is the dilatancy. So, dilatancy in one word, it is mean that when you apply the load or the shearing. So, as I mentioned that if you look at this stress strain curve and the volume change curve. So, what will happen that in the dense sand your volume first decreases, then increases, and loose sand your volume continuously decreases. So, in case of dense sand your volume increases. So, dilatancy means the increase is in volume due to the shearing or the. So, now here because of the shearing where our volume will increase. Now, what does it mean? So, now as I mentioned that we have that our soil which is filled the soil particles, and within the particles if it is a saturated soil. So, as you can see that it is mentioned that dilatancy correction will be required for saturated fine sand and silt, saturated. So, if the soil is saturated, then all the pores will be filled with water. So, and if we now if we apply shearing, if the volume of the soil decreases, then what will happen? The volume of the soil decreases. So, that means your pore water pressure will increase. Now, opposite trend will happen if volume increases, because here because of the dilatancy volume increases, because as I shown you the volume change versus shearing or the strain or the displacement curve, where for the dense sand your volume increases due to the shearing. So, if the volume increases, so pore water pressure will decrease. So, decrease means both the cases, one is first case if the volume decreases, then there will be a positive pore water pressure, and if the volume increases there will be a negative pore water pressure. So, the first is dilatancy because the volume increases, and because of the volume increases your negative pore water pressure will induce. So, now if the negative pore water pressure will induce, then what will happen? Because we know our strength expression is that our shear strength expression is tau is equal to C plus sigma n dash into tan phi in terms of effective stress. So, as I mentioned, it is fine sand and silt, where cohesion we are assume it is cohesion is 0. So, shear strength expression will be sigma n dash into tan phi. So, sigma n is dash is total stress minus pore water pressure into tan phi. So, now as I mentioned that our pore water pressure is the negative pore water pressure. So, what will happen? Now, total stress minus pore water pressure. So, it become plus. So, that means the total stress plus u into tan phi. So, now ultimately the strength expression will be total stress minus plus pore water pressure into tan phi. So, basically your strength of the soil will increase. So, because of this phenomena. So, you will get as the strength of the soil increase. So, you will get the higher n value, but when these things will when we actually construct the foundation or so these things will not happen in the field. So, that is really here during the n value, because we are applying hammer blows, and why it is happen. So, that is why 15, because if the n value is greater than 15, n value n dash is greater than fact 15. So, as n value increases, so that it indicates the soil become more dense. So, if it is greater than 15, so it become towards the dense side. So, that is why the dilatancy will occur and pore water pressure, negative pore water pressure will induce and your strength will increase. So, and you will get higher n value. But when we will do it for the actual foundation calculation design, we cannot consider this effect, that because your strength increases, and so we will not consider that strength increment or strength increase during our design. So, but because of this phenomena you will get a higher n value. So, as we will not consider these things during our design, so we have to apply correction. So, that is the dilatancy correction. So, because of this dilatancy correction, we are basically reducing the n value, and that is why your corrected n value because of the dilatancy is less than the n value which you have which is the n value you got after the correction of overburden pressure. So, that is why these dilatancy corrections are applied in the two cases. In these cases, so it will be a saturated soil, it will be slightly, it will be in the more than 15. So, that in the dense side, so that the dilatancy can occur, and it will occur for your sand, fine sand and the silt. So, the next one that these things I have already discussed. So, the these previous corrections is as per the IS India standard code. You have to apply the two corrections, one is overburden pressure correction, another is the dilatancy correction. But as per the ASTM, American Society for Testing and Material, so they are suggesting more corrections. Okay. So, they are basically we have to apply 5 corrections instead of 2 corrections. So, what are those 5 corrections? So, you can see this is the n dash, dash means again it is a corrected value, and 70. What is 70? So, I will discuss that thing. So, let me explain that why Cn, again Cn is the correction for the effective overburden pressure, and that Cn here we can calculate by these expression, where it is 95.76 by P 0 by. So, as I mentioned, this effective overburden pressure can be shown in different way. It can be P 0 bar, it can be P 0 dash, it can be sigma dash, it can be sigma bar, or sometimes it can be P bar or P dash also. So, here, in this course, in different places, it can be shown in different way, maybe, although I will try to show them in one particular format, but so these all are same. So, that means effective overburden pressure is P 0 dash. So, it is in, as these expression we are using. So, it is in kPa, kilonewton per meter square. So, we have to calculate the P 0 bar in kilonewton per meter square, and we put this value here, and then we will calculate the Cn. That Cn we will use as a correction factor. This is the measured n value, and these are the 4 other correction factors. So, these 4 other correction factors are hammer efficiency correction, drill rod, sampler and borehole correction, and correction due to overburden pressure that we have already explained. So, in addition to other 4 corrections are hammer efficiency correction, drill rod, sampler and borehole corrections. Now, what is hammer efficiency correction? So, here and why it is required, because here we are talking about that we are applying a standard hammer and for to conduct the SPT. Now, suppose if I use different hammer, their energy values are not same for all the hammers, because of because some we are not we are applying these blows in different ways for different hammers. So, our energy is may not be same for all the cases. Now, suppose for a particular site we are conducting say 200 SPT, and we are using different hammers for different site. For a particular location you are using one hammer, and for a particular location we are using another hammer, or our energy is applied. Energy means the applied energy is different for different cases. So, now we have to represent them in a particular common way. So, that is why we have to apply a hammer efficiency corrections, because in all the hammers their efficiency is not same. So, that is why you have to apply this hammer efficiency correction and represent them in a common format. So, now quickly I can discuss you this ER is some energy ratio. So, which is the actual hammer energy that you are applied, and this is the theoretical energy or input energy. Now, this is the theoretical energy, finally, it will be weight of the hammer into the free fall, height of fall. So, this is the input energy, but your applied energy may not be equal to the input energy, because your efficiency is not same for different hammer. So, that is why you are get a ratio, and then for this is the correction for hammer efficiency, this is the ER in ERB. So, ER will get from here, and ERB is the energy that is standard energy. So, this we can represent all the n value in terms of this ERB. That means, we have to convert all the hammer n value for different hammers that we are using in the field, and we convert all the energies to ERB. So, I will show an example, then you will find how we can do all these things. So, and as I mentioned, this ER value, this is different for different hammer. So, this is for donut hammer, it is 45 to 67, safety hammer if it is rope pulley or cat head, then it is 70 to 80, if it is strip or automatic hammer, it is 70 to 100. So, now we will get some hammer efficiency correction. So, now you can see if our ER is 80 and standard energy is 70. So, the correction will be 1.5. 1.14, 80 by 70 1.14. So, now I am finishing this class here. So, in the next class I will discuss about the other corrections factors which is required as which is recommended as per the ASTM, and then I will solve 2 problems for one as per the IS code and one as per the ASTM code to show you how we can use these corrections. Thank you.